Apologize for not having the exams ready to return, but there are outstanding makeups. So hopefully that will be taken care of this afternoon. And I'll be able to give them to you all Friday. Grades will be posted as soon as I finish grading the makeup exams. But that means I need to finish our discussion on probabilities. So in a large number of the problems I gave you, I just gave you a probability, or we derived it from other information we knew about the problem set. If I want to keep using our theoretical probability, definition for the probability of an event, we have a formula for that from a theoretical standpoint. We gave this last week before the exam. What's the definition of the probability of an event? We have our empirical definition, we have a theoretical definition. Yes. That was our generic definition. There was an actual formula for the probability of an event shortly under there. That's the general definition. There was a specific formula one. I think I wrote P of E maybe instead of P of A. My event.
Is it P of A equals A over S?
Not just A over S, there was something to that, right? There were symbols around that. A over S.
The absolute value.
Right. And what do those absolute value bars mean for a set?
Is it a number of sample events?
So that's the size of that set. So I need to know how to count how many events are in my sample space and how many events are in the thing I want to look at. How many simple events. Now, for some of the things we were doing, this was really straightforward. Here's a deck of cards, pick a card. How many options are there?
Maybe 52.
Presto. Here's a coin, I flip the coin, how many outcomes are there?
Only 2, heads or tails.
That's it. But as my events get more, my experiments get more and more complicated, my sample spaces get larger and larger. How do I count how many things are in the set S? There are a lot of distinct counting rules. I want to start with the most basic, the fundamental counting principle, or the fundamental rule of counting. let's suppose I'm really not looking at a single draw a card, or a single coin flip, or a single roll of the dice. I'm looking at multiple. Start with 2. If I have 2 events, event 1 happens in whatever many ways, number 1. Event 2 happens in n2 ways, then both A and B. I want both of them to happen. How many different ways can that happen? Well, it's one from column A and one from column B. So n1 times n2 ways. This seems kind of dumb until we start to put it into a context. So how many different Pennsylvania license plates are there? That's how many different license plates are possible. Wait a minute, what's Pennsylvania license plate look like? They just changed the design of a license plate, but they didn't change the format of the tag number. A license plate is 3 letters followed by 4 digits. There used to be, on the old plate, a little keystone for the Keystone State in between these 2. They got rid of that and they put a little Liberty Bell on the background of the plate. So newer license plates don't have the space in between the letters and the numbers where there's a keystone. They just have the letters and numbers right up against each other. Hold that thought, Liam. I'm trying to fill in 7 different choices. So I'm going to think of these as if they are 7 different events. And I'm going to count how many ways each one could happen. So, Leo, talk to me about this spot.
So with the letters, I know there's 26 letters, there's 3 spots, so that could be a 26 cubed.
Well, let's just write it separately for each spot, right? I want all 3 spots filled, so I want you to fill spot 1 and spot 2 and spot 3, and that word "and" tells me I should multiply those together. Then when I get to digits, Leo,
It would have to be 10 times 10 times 10 because it's a 0 to 9. That'd be 10,000 for the digits. There's 10,000 different combinations.
just for those, plus the 326s there, if I multiply all these together, I get $175,760,000 license plates possible. You could legitimately give every human being in the state of Pennsylvania their own license plate and staple it to their ass. And you would have a whole lot left over because the population of the state of Pennsylvania is about 13 million people. I've got 175 million license plates. This is why license plates cycle in and out. The newest license plates are being given, I'll start with the letter N. When I moved to Pennsylvania and I got my car title transferred here in 1992, my license plate started with an A. We moved quite a ways through the alphabet, but that means somewhere around 30 more years from now, we'll have done all of them and we'll have to cycle back around. By the way, there is a problem here. Legitimately, there's a problem here. I have not made any exceptions. I'm allowing any combination of letters and any combination of numbers. And that means that you could get something that spelled out a rude word, or that spelled out an odd combination of numbers, right? I'm pretty sure no one wants to. Well, I know probably somebody does want the license plate that reads XXX6969. And if you gave a 16-year-old a license plate whose numbers were 6767, they might just lose their minds. I am quite particularly reminded of this because I grew up in the state of Florida. The state of Florida had license plates that were 3 and 3. But you could mix letters and digits anywhere. And I got behind a car whose license plate read A55RG4. There used to be a keystone in the middle of the floor of the Pennsylvania license plates. Do you know what's in the middle of a Florida license plate?
Peach.
That's Georgia. Georgia's get peaches. Florida gets oranges. No. They should have caught that right away and thrown that license plate out. But let's take this and make it a little more practical. Passwords. You have a password on your computer. What is the requirement for your password? Interestingly enough, modern computer passwords have gotten more and more complicated. But when passwords started, they were just uppercase letters because the computers couldn't differentiate between uppercase and lowercase. So let's make a simple password. Just going to use letters, and I'm going to make it 8 letters long. How many passwords are possible? Who said that? It was the right number, but who said it? Mumble, mumble, mumble. Oh. There are 8 spots. Each one has 26 options, right? So I'm going to get 26 to the 8th, which is not a small number. Again, you've got a calculator. What's 26 to the 8th? Jacob?
Bounding, it's 0.09 times 10 to the 11.
So let's see. Million is 10 to the 6th. Billion is 10 to the 9th. So that's 209 billion passwords. Hang on a second. Your computer is capable of running 1 billion operations a second. That's what gigahertz means. Which means it would take me 209 seconds to run through all these passwords if I could do one password at an operation. 209 seconds is 3 minutes. A password like this is fairly weak if it takes me only 3 minutes to get through all the options. So let's up the number of options. If I add lowercase and uppercase letters, because now we can tell those apart, what happens to all those 26s?
Maybe 52 to the 8th.
And 52 to the 8th? Just give me the 10 to the whatever.
5.35 times 10 to the 13. That's rounding at the 2 places.
Okay, but 10 to the 13th, I've gone from billion
Trillions.
to trillions. Add numbers. Digits, right? There are 10 digits. I've now gone from 56 to 66. Add special characters. The exclamation point. I can't use the @ symbol. I can't use the number sign. They're reserved for some things, but I can use all those extra keys. Let's say I get another, I don't know, 10 or so. I'm now at 76. Let's make the password longer. Instead of 76 to the 8th, I make it 76 to the 12th. These numbers get mind-blowingly huge very quickly. I can't use this idea directly for drawing a card. Because if I say, here's a deck of cards, take 2 of them, what happens? You take your first card, how many choices are there? Deck of cards. How many choices for your first card?
52.
But then you're going to take another card. There aren't 52 choices again, aren't there? So I changed this. If I'm not allowed to put the card back in the deck. We talk about this idea as an ordered selection without replacement. I've got 5 people, and I want to put them in a line. How many different ways can I put 5 people in a line? Hold that thought there. Let's go through our choices. If I write these 5 people, the spots in the line are right there. How many choices? Who goes first? But does person 1 have to go first? But there are 5 choices, right? So there are 5 choices here. But now that person's already standing, right? How many choices are there for the next group, the next person? I've got somebody already standing. I can't put them in the second place. They're already in the first spot. So my number of choices went down. Same thing here, right? I've already got the first 2 people. And then I've got the first 3, so there are only 2 choices left. And then there's only 1 choice for the person at the back of the line. This sort of descending behavior, which, by the way, if I multiply all of these numbers out, I get 120. We're going to abbreviate this as 5 factorial. You don't read that as 5. The exclamation point is not for emphasis here. It's a math operation. In general, if I have n factorial, I think of n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. If I think about a deck of cards, there are 52 cards, right? So if you shuffle a deck, that's putting that deck in an order. How many ways can you order a deck of cards?
It would be like 52 factorial.
Okay, wait a minute. Depending on your calculator, you may or may not actually have a separate button with an exclamation point on it for factorial. I have one of these graphing calculators. The factorial is hidden. In order to get the factorial, I need to hit the math button. So I'm going to start by typing 52 because I want to do 52 factorial. I hit the math button, and all the way on the right end of that top menu bar says PRB. That stands for probability. So if I go over to that option, I see an exclamation point, option number 4. And if I hit that option, that will put the exclamation point at the end of whatever number I'd already typed. So if I hit enter, it's going to give me 52 factorial. Now, I would like to point out to you the size of this number. That is an 8. And then I have to move the decimal place over 67 times. How long do you think it takes to shuffle a deck of cards? I just want to shuffle it. How long do you think that takes?
Maybe like 30 seconds.
Probably. Like a half minute. So let me make it incredibly fast. I'm going to shuffle a deck in a second. I would like you to get on the internet and Google for me. Age of the universe in seconds. What number do you have for me, Zach?
436 quadrillion seconds.
Okay, quadrillion. Hang on a second. Million, billion, trillion, quadrillion, right? So 10 to the 6th, 9th, 12th, 15th, 400 would be 4 times 10 to the 17th.
Yeah. 4.36 times 10 to 7.
This is way more. This is a billion, 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 billion times the life of the universe in seconds so far. If you shuffle a deck of cards, it is most likely that you are bringing something into existence that no one ever else has seen before. Because the chance of 2 decks being shuffled exactly the same way are 2 in that number. There aren't enough seconds in the life of the universe so far for 2 decks to have been shuffled the same way. Unless you're a card shark and can force decks into certain patterns. That's not shuffling a deck, that's doing sleight of hand. If you do 70 factorial on your calculator, what happens? By the way, if you want to recreate the last thing you did, hit second and enter, and it'll bring back the last command, and then I just change the number. What? Overflow? My calculator only understands numbers up to 10 to the 99th. 70 factorial is 10 to the 101st. It's too big for a calculator. I only need to have 100, fewer than 100 people to line them up to a number that's so big my computer won't handle it. It's insane. But I can think of this as an ordering. And that's the important part in my head. These are ordered behaviors. Oh, I really want to add one more thing. This formula that I've got here for n factorial only works for positive numbers. 1 factorial, 2 factorial, 3 factorial. It is useful for me to think of ordering no items. I have right here in front of you all of my Olympic medals. All 0 of them. And they're in order on this table. The order is empty. Yes? So that's 1 away. I gave you an empty ordering. The reason I bring that idea up is going to come up in a formula we're going to use in a couple minutes. So 0 factorial is defined to be 1 to make my life easier. Questions? Yes, sir.
With this fundamental counting principle and ordered selection level replacement, we are counting for the S
Right.
size.
I'm
right?
counting for the S size. Or I could be counting for the A size because I can use them together, right? Let's think about, I want to roll dice, right? If I think about the ways in which something can happen, let's say I get an even number on the first die, and I get an odd number on the second die. How many ways can I get an even number on the first die? The normal standard die, there are 6 options, 3 of them are even. Same thing for the second die, there are 3 odds. 3 times 3, because I want both of them to happen at the same time. Isn't that the fundamental counting principle? So I could just be counting the A or the S. I just came up with 9, right?
Yes.
How many ways are there for me to roll 2 dice and anything to happen? So my probability is 9 out of 36. I got both A and S using that fundamental counting principle. And then I was able to find a probability. A priori, in advance, without any decision of actually running the experiment, a purely theoretical calculation.
Okay, thank you.
Absolutely. So what if I'm looking at smaller things, right? Because really, that's all an event is. It's a subset of my sample space. I can do a lot of different things. But the same idea is going to come up of order. There are 17 of you in the room right at the moment. Let's suppose I am going to give out a first place, a second place, and a third place prize for some competition. In this group of people, how many different ways could I have the podium set up? I'm going to use the fundamental counting principle. But since I'm doing a first, a second, and a third, the order in which I select these things matter. Please hold that thought. Let's write it out just like we did with the previous setup. Like I was standing people up in line. How many choices are there for that first place? 17. But now there's a person who's no longer sitting in the room. 16 and 15. Okay. That's the answer, by the way. I don't know what this number is, but that's the answer. I would multiply all three of these things together, and I would get the answer. But there's another way to think of this. I could line up everybody, right? And then take the 4th through 17th and tell them to go sit back down, right? Does it matter then how those people were ordered? They don't count. They're equivalent whether they're in any given order. Only the order of the first three matter. So the other way I could think of this is I could think of taking everybody and chopping off the last 14. Chopping off in this case, I'm going to divide so it cancels out. Now, why would I write this way? I'd write this way because both of the expressions here are factorials, aren't they? That top number is 17 factorial. And what's the bottom number? Leo?
14 factorial, but I would be using n minus r.
Hold that thought. It's 14. I just wrote it as 14, but 14 is 17 take away the 3 that I had at the top. I like this. I like that formula a lot. Because this is ordered, we're going to call this a permutation. And we're going to write NPR out of n things, pick r of them. I use that word pick deliberately because I'm picking them one at a time. And then a formula for this is exactly what we just came up with, n factorial over n minus r factorial. I'm playing cards. Maybe I don't get all the cards. Somebody pick a card game for me. Bridge, poker, blackjack, we'll pick a card game, right? What?
Blackjack.
Blackjack. I get 2 cards to start with, right? If I get those 2 cards, then I really only care about getting 2 of them. So I would do 52 P2. And that would be 52 times 51. Please note, I'm being deliberate in saying these are ordered. Because when I'm the dealer, the first card I get stays face down, the second card is face up, so they're different. And I know in advance, a first and a second, the order matters. That's why I use this formula. But I can't repeat a card. If I'm using one deck of cards and you get the Jack of Hearts, no one else can get the Jack of Hearts. There's only one in the deck. So repetition is not permitted in this setting. If repetition is permitted, I need to use the regular counting rules. I can't use this idea. But if I'm
I have multiple decks.
whole different ballgame, and then I am going to use the counting principles, but in a repetition limited fashion. There's a lot to that. There's something called a multifactorial or a multi-permutation that allows for that sort of limited repetition behavior, where you have distinguishable objects and indistinguishable objects. Because I can't tell one Jack of Hearts from another Jack of Hearts, and maybe I've got 6 decks. And in 6 decks, that's really hard to keep track of, which is why most dealers at casinos use 6 deck shoes, because it's hard to keep track of. Not impossible, go watch the movie 21, but difficult. So, if I am a player at that blackjack table, I get both of my cards face down. How do you know which card I got first? Once they're in my hand, I could move them, right? Does the order in which I got the cards matter? If you get the Jack of Hearts followed by the 9 of spades, it doesn't matter which one you got first or second. You've got 19 as far as blackjack is concerned. So the order in which the cards were dealt to me doesn't matter. This formula is not going to account for that. If I have an unordered selection, then let's use the card example for the moment. The Jack followed by 9 is the same as the 9 followed by Jack, right? So those 2 things should only get counted once. So in that number, 52 times 51, I had 2 times as many ordered selections as I do unordered selections. Every pair of cards is going to appear first in one order and then in the other order. But they're all going to get matched up that way, aren't they? So I would say that what I want to do is I want to reduce my number of options by the number of ways I can order my subset. Wait a minute. Ordering a set. Putting things in order. That's a factorial, isn't it? So if I got 2 cards, I could put them AB or I could put them BA. That's 2 factorial, 2 times 1. If I got 5 cards, that would be 5 factorial. That's 120 ways, right? If I got 13 cards, if I'm playing bridge, I could reorder them in 13 factorial ways, playing hearts. I have options to put those in order, but it's going to make this number smaller. So I'm going to divide again. And I'm going to divide by the number of ways I can order the things I got. But I got R items. So I'm going to divide this number by R factorial, which is the same as saying that I'm going to get now an extra R factorial on the bottom of my formula. I'm dividing not once, but twice. This is known as a combination and is written NCR. By the way, this is why I hate the phrase combination lock, because the order matters in a lock. Now, I will normally read this C as N choose R rather than N pick R. And to me, that C shape, if I make that C shape with my hand, I can think of just scooping them all up at once. So the order in which I got them doesn't matter, as opposed to picking them one at a time. So I think that kinesthetic helps. You will also sometimes see this symbol written like this as a binomial coefficient. If you never see that, I don't care, but that means NCR. It means the same thing. If I go back to my students and I'm selecting out of 17 of you, instead of a first place, a second place, and a third place, 3 of you get a $10 Starbucks card. I don't know what it is either. We'll leave the book. Then it doesn't matter who gets the first card, who gets the second card, who gets the third card. Oh, you're a stink button, aren't you? Oh, well. Since all the cards are equivalent, it doesn't matter who I pick first or second or third. I'm just going to give you all the same thing. I would use this instead of the NPR. So instead of 17 over 14 factorial, it's 17 over 14 factorial. Take that number, divide it by 3 factorial. Because the order I select the names in doesn't matter. Lottery tickets work this way. Quick. Pennsylvania Lottery is online. So go to the Powerball website, powerball.com, and tell me how you play the Powerball. How do you fill out the tickets? How do I do it, Cole?
Says select 5 numbers between 1 and 69 for the white balls, and then select 1 number between 1 and 26 for the red Powerball.
Okay, wait a second. So it's 2 sets of choices with the word "and" between them, isn't it?
It says then.
You fill out your card. And you turn it in, and they print out something for you, right? And then you wait until the drawing, and if all the numbers match, no matter what order they come out in, because they're just going to have a barrel full of balls, and they throw out the 5 white balls, and then they have 1 barrel full of red balls, and they throw out the 1 red ball. But that means if the number 17 comes up and it's on my ticket, I don't care if it came up first or fifth or fourth or second, it doesn't matter. The order in which my numbers come up doesn't matter. So this selection, 5 from the numbers 1 to 69, is a combination. It's 69C5. And then, and. What do I do when I hear the word "and"?
Multiply.
I multiply. Out of the 26, I have to choose 1. Now, it's 1 ball. If I choose this doing P1 or C1, I'm going to get the same result. Because what's 1 factorial?
1.
It's just 1. So I can actually work this out. Grab your calculators. What's 69C5? Wait a minute. C, we did all these factorials by hand. Go back to that probability menu. Math, PRB is over here. Hey, wait a minute. NPR, NCR, they're built right in. So I have to type the number first. So I'm going to quit out of this. I'm going to go 69, math, probability, 3. And I'm going to ask it to choose 5. And it does the whole thing for me. Now that's just the white balls. Then I'm going to do 26, choose 1. I'll go back here and I'll change the numbers. But there are only 26 ways to do that, right? So I'm going to take this number and multiply, not subtract, multiply by this number. That's how many different lottery tickets there are. 292,201,338. Which means if you buy a Powerball ticket, your chance of winning is 1 in that much. I would like to give you a little bit of a comparison. What's the chance you get struck by lightning? I wish I was making this number up. The chance to get hit by lightning is 1 in 15300. The chance you get hit by lightning is 1 in 15,000. What's the chance you get hit by lightning twice? Chris?
That's all.
Well, I would hope so, right? I hope that you have to be pretty unlucky to get hit once, then you're going to get hit a second time. Wait a minute, I want to get hit first and hit a second time. What should I do when I hear the word and?
Multiply.
And each one of those numbers is this, isn't it? So it would be to hit twice, it would be 1 over 15,300 times 1 over 15,300. What's 15,300 times 15,300?
234 million, 90,000.
Wait a minute, 234 million?
90,000.
0.90000. This is a bigger number, isn't it? The Powerball number. That means you are more likely to be hit by lightning twice than to win the Powerball. A lottery is a tax on people who are bad at math. Almost all of the questions I am going to get asked require me to count up the number of options and then to figure out how many ways can something happen for me. Notice this multiplication right here came from our fundamental accounting principle. What I used the probabilities, did not. Because they're independent events. The probability of A times the probability of B. Getting hit by lightning once, getting hit by lightning a second. So we have all these rules, and now we can count probability. And that means that I can do all these theoretical calculations in advance. As long as I can count big enough sets. And since most of the time I'm dealing with unordered sets rather than ordered sets, card games, I'm probably not going to care how the order of the cards comes to me. I'm going to care about which cards I have. So I'll use that C number more often. Poker games. 52C5. I get 5 cards in a poker game, right? I mean, I get them all at once, but I only get 5 cards. What's 52C5? Leo,
2,590,960.
2.6 million. And that's without care to order, right? Okay. The best possible hand in a poker game. Anybody play poker? I'm not going to tell anybody outside this room. If you've played poker before, the best possible hand in poker is a royal straight flush. A royal straight flush consists of a 10, a jack, a queen, a king, and an ace, thus the royal part. Straight, they're in order. Flush, they're in the same suit. So not only do you have to have 10, queen, jack, king, ace, you have to have them all be spades, or all be clubs, or all be hearts, or all be diamonds. That means there are only 4 possible ways to do that. Congratulations, you just figured out the probability of a royal straight flush. 4 out of 52C5. That's the chance it happens. Which, by the way, works out to about 1 in 650,000. So if you play 650,000 hands of poker, you should get 1 royal straight flush. Maybe. That's where it comes into play, Alessandro. I'm going to count the number of ways I can get what I want, the number of ways in my sample space, and that's it. That's my probability calculation. The unfortunate side of this is it means we have to read the problem carefully and decide, are they asking where repetition is permitted? Are they asking where order matters? That will allow me to narrow which formula I want to be using. Questions? I use games most of the time to talk about these ideas because most people are familiar with them. These same exact procedures and principles go with insurance. You all, if you have a vehicle or if you drive, you have auto insurance. You have liability insurance, you have property damage insurance. If you drive, you are required by Pennsylvania state law to have these things. How much should I charge you for your insurance? Well, what's the likelihood of an accident that causes this much damage, or this much damage, or this much damage, or holy crap? Once I figure out the probabilities of all of those, I can figure out what I should expect to happen, how much I expect you to cost me as a driver if I'm the insurance company. This idea of looking at all the possible things that could happen and figuring out probabilities associated with each one is called a probability distribution. And that is the basis of all of our statistical analyses. What should happen? Then I look at what actually happened and I say, how likely or unlikely is it that what should happen and what did happen match? And we'll be able to say, oh no, this was unusual, this was weird, this was perfectly understandable. Probability distributions are what I will build starting on Friday and once we get back from break. Now that does mean that we have finished chapter 5. And as such, means the chapter 5 homework is due 2 days from now, 2 class periods from now. What class period is that?
When we get back.
The Monday we get back from break. People do the homework before you go. That way you can spend your break relaxing and not worry about this crap. We'll see you all on Friday. Have a wonderful rest of your day.